Okay, hello everyone. Right, so we're going to review a little bit on the box model, which is what box model is what we're going to do today. And we're going to review a little bit about the experiment that we did last time. And the experiment that we did last time was on anchoring, where we had two different groups. Remember that? Okay. So to review what we did last time, what was the condition in that experiment? We had an anchoring. We have two groups of people. We had a group of people who had 11, and the other group of people who had 73. Okay. So there's three things I want us to review. One is called condition, and the second thing is the response, and the third is the units. So what was the condition of that experiment? Someone. What was the purpose of that experiment that we did last Friday or last Wednesday? We had two different groups, and what were those two groups? Remember? You either got the what? The 11 or the 73. And that's called the condition. Those are the two factors. We want to compare those two groups. Okay. What was the response variable that we were interested in doing in that experiment? What was the response? Yes?
The percentage of what you thought the percentage is after taking credit score, whether it's less than, greater than.
That's right. It was the percentage of countries in African countries in the UN. And we wanted to know whether if you were given a initial number like 11 or 73, would that affect your number? Okay, and we're going to go over that. We're going to give you the data today to show you how you responded. Okay, so the response was the number, and we wanted to know whether did that have an effect on people? By giving you an initial value, even though we said that number was completely randomly generated, which was not really true. But we wanted to know whether that number would cause you to either give you a higher number or a lower number. And what was the units? How do you define the units again? Yes, anybody? Anyone else? What were the units? Yes? That's right, students and stat 20. Very good. Okay, so that's what we did last time. Okay, and this is exactly what she wrote. This condition 11 through 73, students and stat unit, and the response was the percent of African countries. All right, so what Professor Nolan did was she summarized the data, and here it is. The anchor is either 11 or 30. The 29 and 30 are the frequency. 29 people responded, got the 11, and 30 people got the 73. So this is not so interesting yet because we're really interested in comparing the two. But here's a summary of all the information together. You can see that the minimum is 2, the maximum is 100. Does that seem strange, 100? Somebody thought 100% of the countries in the UN was 100% of the countries in the UN are African countries. So that number, and then there's two people who responded with NAs. But this is the summary data of everything together, okay? And what we're really more interested in doing is comparing the two groups, as we'll see. So when we compare the two groups, we could either, draw two density plots, as we did in your homework assignment. But because we don't have a lot of data, we're going to do either boxing whisker plots or strip charts, okay? So here it is, okay? Here are two strip charts. One is the top one is 73, and the bottom line is 11. And I want you to take a look at this for a moment and try to name a couple things that distinguish the two groups, the 73 from the 11. Okay? So look at that for a moment and tell me some features of these two. And how do they differ? How are they similar? Okay? Somebody? higher maximum value for which group? 11. For the 11 group, okay. Well, not with higher, okay. So the 73 looks like there's more in that one mode, but if I compare the 73 and the 11 group, we want to compare either means, medians, or mode between the two. And what are those things called when you compare means, medians, and modes? They're called what? Those are summary statistics, which are measures of central tendency. Okay? So if I look at measures of central tendency, which one has a larger measure of central tendency? The 73 group or the 11 group? Which one has a higher one? By looking at the strip chart, it looks like the 73 had a higher average than the 11. So if you look at the mean or the median or the mode, it looks like the 73 group had a larger in terms of all three measures. Okay. What else can you tell me about these two charts? What would you rather compare, the mean or the median? What would you rather look at? The mean or which one? Median. Okay. When you look at the mean of the 11 group, one of the things that's going to be kind of that'll be calculated into the means will be these numbers right here. There's 100, there's a 90, there's maybe like a 78, and those either the people who answered those questions didn't understand the question, or they were just writing anything down. Okay, so you got to be careful when you look at this data like this. And if you try to compare means, the means will be affected by these numbers right here, and those are outliers, or they don't really make sense. Or the people who answered this probably, I'm not going to put you on the spot and ask who actually set those. Okay. But if you compare averages, you're going to weigh those numbers in, okay? So that's something to be aware of. What type of skewness do we have in both of these charts? If I want to talk about skewness, are these symmetric? So we have a long what? Yes.
Well, I think for 11, most of the information is kind of concentrated in 4.
Mm-hmm.
But 73 is a little bit more spread out.
Okay, that's right. So you're thinking that the 73 has a maybe larger variance, and there's more in here. This actually may have a large variance because of these outliers, but other than those, which you kind of wonder about what people were when maybe they didn't understand the question, but you're saying that most of these are closer. Okay, all right, good. So when you look at these, you could also say that in both cases they have a long tail, a long right tail. Okay. Well, let's look at some of the statistics as well. Let's look at one more thing. Here's a box and whisker plot. Okay. And if you look at this box and whisker plot, are there any additional information that you can see from this box and whisker plot? To remind people, for the box and whisker plot, the bottom part of the box is called the what? It's called the what percentile? 25th, very good. And the line is called the what? The median, the 50th percentile. That's right. So if you look at the group 73 or group 11, the median over here is closer to the 25th percentile, to the first quartile. Okay. So the 73 group, the median is not in the middle of that box, so that indicates that there's a little bit more skewness in this group, in the 73 group. So that's a way to look at this box and whisker plot, is to look at that median line and see whether it is in the middle of that box, or like in this one, or closer to one quartile than the other. The other thing is, again, you can see those outliers really clearly that are above the whiskers. All right, so here's what we're more interested in. So these are the summary statistics comparing the two groups of people, okay? Comparing the two groups. And as we said, all three measures of central tendency, which are mean, median, and mode, they are higher or lower for the which group? They are, for the 11 group, they are lower, right? So for example, if you look at the 11 group, the median is 15. If you look at the 73 group, the median is 23. That's a difference of 8. What happens if you look at the mean? The mean in the 11 group is 22, and the mean in the 73 group is 27. So that's not quite as dramatic, okay? And why is that again? It's because of what we said before. There are those numbers which are like hundreds and stuff and 90s, which really don't make sense. So the mean, if I were to try to compare the two groups, maybe the median would be a better measurement to compare the two groups rather than to look at the averages, because the averages are quite affected by those very large numbers. Okay, so whereas if you look at the median between the two groups, you can see that this difference is greater when you look at the two medians. Okay, and all right, so those are different ways to look at those summary statistics. All right. Now that we see an 8-point difference in the median, okay, the question that you're always asking would be, is that difference statistically significant or not? I mean, it could have just happened by chance. Maybe there was really no difference at all between those two groups, and we just saw a difference of 8 just by chance, just by random chance. Okay? So how do we figure that out? Okay? So essentially, we're going to talk more about this and saying we're going to set up a null hypothesis and an alternative hypothesis. We'll give you more formal languages later on. But right, there are essentially two different positions. One is that the difference between those two groups is just due to randomness, it's just due to chance. And the alternative is what? Is that if you anchor at where you're given a larger number like 73, people are more likely to say to give a higher number, okay? And then when the people who are in the other group, the 11 group, those people are more likely to give a lower number, okay? So that's the alternative hypothesis, and you want to be able to say, does this data show? Does this data can you reject that null hypothesis and believe in the alternative? We want to know, is this evidence compelling enough? Okay. So that's what we're going to talk about today a lot. We're going to talk about in terms of using a box model in order to figure out how much chance variability can we understand in a situation like this. Okay. So let's go ahead. We're going to go back and talk about the 3 types of errors that you have in an experiment. Okay. So one is the difference in those two groups where, there's the wanted one, which is we purposely gave one group all the 11s, another group all the 73. We were hoping to see a difference between those two groups. That's what we wanted. Okay. Measurement process. There could also be errors due to that. Well, if we couldn't read your writing too well, or if people didn't understand the question, those are measurement errors that we don't want, and those are the unwanted ones. Okay. All right. But the errors that we talked about, there's a chance variability. And that type of errors is unavoidable, but we actually can't handle this part. So if I'm talking about the error in terms of random variation, in terms of somebody could have gone to the 11th group, or somebody could have gone to 73 when you draw out a particular ticket, that part we should be able to figure out, and we're going to talk about how we're going to be able to talk about how those numbers come about, okay? So the whole point is that if you make 2 measurements under the same condition, okay, you're likely going to get different numbers. So those of you who've taken chemistry, a lot of times you make 3 or 4 measurements, and what do? You take the average. It's not because the thing that you're measuring is changing, but every time you make a measurement, you're going to be off by a little bit. So a lot of times we want to figure out how much those things are likely to be off. Okay? So we're going to model this with chance error. Okay? And that's the part that you can live with. And we're going to see how to reduce that chance error in some ways by taking a large sample. Okay? All right. So the measure value that you're looking at when you're measuring something is equal to the true value plus some type of chance error. And the chance error has properties that makes it possible to learn from an experiment in terms of sometimes the chance error could be overestimated, sometimes it's underestimated. But if you get enough of a sample, it should even out, hopefully. Okay? If they don't even out, then there might be a bias, and that's where we go back to that previous chart. If you have an unplanned systematic error, then that would not be. Then that's when you have a bias. Okay, but the ones if there's no bias, and you're looking at the chance error, hopefully sometimes you might overestimate and sometimes you might underestimate, and in the end it should balance out to 0. Okay, so we're going to look at on this next slide how some could be positive, some could be negative, and for the most part they should cancel each other out. Okay, we're going to model this using a box model, where we're going to model this using where we're going to put some errors in that box, and some of the errors will be positive, some will be negative, and what you should see is that the more measurements you make, on the average chance error will go down. Okay, that is why like if you're doing your chemistry experiment, they tell you to make maybe 3 or 4 measurements, and you take the average of it instead of just doing 1. Well, every time you make more measurements, the average chance error will start to go down, and we'll see why that happens. Okay, and if you want to figure out how big that chance error is, one way to estimate it is by looking at the standard deviation of a sequence of repeated measurements under the same conditions. And that's why we talked about, if you're doing a chemistry experiment, you might be measuring something more than once, and then hopefully things will balance out. Okay, so we're going to do an experiment with this. So let me go to this document camera. Okay, so these are 4 chance errors that I'm gonna put in here, and I'm gonna have one of you volunteer to come up here to pull something out. Now, if you pull a 1, that means that your measurement is off by 1. And if you in the positive side, if you pull a -1, that means you've underestimated something, and if you pull a 0, that means you got it exactly right. Okay, so we're gonna look at we're gonna see how this can be modeled. So remember when we looked at the previous slide, the actual measurement is the actual value is equal to the measurement plus some type of chance error. Okay, so I'm going to put these 4 things in here in this box. Then mix them up, and then we're going to talk about more complicated boxes in a moment. Go back to here. So we're going to pick these errors from this box, and again, the measurement is equal to some exact value plus the error that we get from here. Okay? All right. So I'm going to mix this up, and I'm going to ask, why don't you draw one? Can you draw one from here? Okay. And before you, just draw one. Yeah, go ahead and draw one. And don't before you tell everybody what it is yet. So what's the chance, and what's your name?
Johnny.
What, Johnny?
Johnny.
Johnny, okay. So what's the chance that Johnny drew a 0? What's the chance he got the answer exactly right, which means drawing a 0? 1/2, 50%. Okay, very good. And the reason why it's 50% is because there's 4 tickets, okay? And 2 of them are 0, so therefore 2 out of 4 is 50%, okay? He could have also, there's a 50% chance that he could have got an incorrect answer by overestimate. He could, if he drew a 1, he would overestimate by 1. If he drew a -1, he would underestimate by 1, okay? So let's see what you actually got.
0.
You got a 0, so he actually got it right, okay? Very good. Now, you can imagine what would happen if you drew this many, many times, and we're going to see about that. So by the way, what was the chance that Johnny drew a 1? If he were to draw a 1, what would that probability be? 25%, okay? So those are the theoretical probabilities, but if you were to do this experiment, let's say 100 times, let's say you go ahead and do this experiment 100 times, you don't expect to get exactly 50 zeros, 25 ones, 25 zeros. If you were to draw this experiment 100 times, you might have gotten maybe 53 zeros, maybe you might have gotten 24 ones. There's going to be some randomness in here, okay? And that's called the empirical distribution. And we're going to go through, when we look at this more complicated box, we'll see how that works, okay? We're going to compare maybe like an empirical distribution to the theoretical distribution. Okay, so this is a theoretical distribution. Again, you can see 50% 0, 25% 1, 25% -1, okay? And if I asked you, on the average, how much will you be off by, okay? Now let's just say, when I say off by, we're talking about the absolute value, okay, of that difference. You're going to be off by, on the average, 0.7, okay? So it's 0.67, because on the average, you're going to be off by 2. It's going to be absolute value of 1 plus absolute value of -1, so that's 2. And so, and then the other ones are 0. So on the average, you're going to be 0.7. You're going to be 0.7 away. Okay. So, and you'll notice that you'll never be exactly 0.7 away, because you'll either be 1 away or -1 away. Okay. But on the average, you'll be 0.7 away. Yes. She probably calculated the standard deviation of those numbers. Okay, so if you look at 0, 1, and -1, and you calculate the standard deviation of those 4 numbers, the standard deviation will be roughly 0.7. Okay, now let's look at this box. Okay. There should actually be 2 more. There's a total of 12 tickets in this box right here. Let me show you. There's actually another one. There's 2 1/2 and 2 -1/2. But that's what this box looks like. There's a total of 12 tickets. I think there's 2 missing ones on this diagram. But the average of this is 0. Okay, the average of all these tickets are 0. And if I scroll down, this is the distribution of that box. Okay, so there's 2s, there's 1s. Most of them are 0s. So there's a total of let's go back to that previous one. There's a total of 4 zeros, right? There's a total of 4 zeros. There's a 1. There's a -1. There should be 2 -1s and 2 -1/2, but this diagram doesn't show that. But if you look at this distribution here, this tells you what that looks like. And again, on the average, this is 0. Okay, if you take the average of all those numbers. All right. So right now, what we're going to do is try to calculate how likely the average when we pull tickets out of here. How likely we're going to pull 1 ticket first, and then we'll pull another 4. How likely is the average going to be a certain number? Okay. So if I scroll down here, okay, this is how you would do this in R. in R, you could actually put all these numbers in. You could actually say box equals C for concatenate or combine. I combine all those numbers, and then when you hit the command sample, when you type in sample box comma 1, it draws a sample of 1 from that box. Okay, and every time we're drawing a different 1. So this is a way to simulate data in R. We're going to also simulate it here as well by putting all these numbers in. And I'm going to take out the other 4. And if I'm in R and I say simulate, so what I'm doing there is I just gave it a name. I call sim1 equals the sample box 4. So right now I'm just going to have you pick 4 numbers instead of picking 1. Okay. And the way that I'm doing it right here in R, because I'm sampling without replacement. So if I go sample box comma 4, I cannot put a number larger than 12 because there's only 12 tickets in here. Okay. In the next slide, I'll tell you that there is a way for you to sample with replacement, and you just have to add another option in there. But so if I go ahead and pick 4 numbers, okay. So go ahead and pick 4 numbers and calculate the average of those 4 numbers. So 1, 2, 3, 4. And go ahead and tell what numbers you got.
Negative 1/2, or negative half, half, 0, and 0.
Okay, so yeah, so you got 0, 0, minus 1/2, 1/2. Very good, thank you. So everything balances out, so you actually got the right answer then. Okay, so that sums to 0. Here's the case. If you wanted to do this in R, the way that you would approach this is you would say, look, sim1 equals the sample box comma 4. Sim1 is just some name that I created. And then when I hit sim1, those are the 4 numbers that I got in my simulation. And then I go mean of sim1, that will give me 0.25. Okay? And again, I do it again for another case. And this time I got, the second time I got minus 2, 0, 0.5, negative 0.5. And again, this time I got a mean of negative 0.5. So my question is, if in a sample of size 4, what are the smallest and largest possible sample means when sampling without replacement? So let me go back to the previous slide so you know what are the numbers. Okay, maybe I'll look at it right here. So the numbers are minus 2, minus 1, negative 0.5, negative 0.5, 4 zeros, a 0.5, 0.5 again, and then 1 and a 2. So if I pick 4 numbers from here, what is the largest possible average? How do you calculate the largest possible average? What would that be? It would just be 0.5 plus 0.5 plus 1 plus 2. So that's a total of 4 divided by 4, right? So your largest possible average is what? It's 1. And what is your smallest possible average? Minus 1. Okay, but on the average you should get roughly 0. Okay, so we can figure out what are the largest possible and the smallest possible based on this. All right, now let's go back. Another way that I could sample. I could also sample with replacement. So here I don't just have to sample 4. I could have sampled 50 now. Because every time I pull a ticket, I actually put it back, okay? So in this case, I got 2, 2, minus 0.5, and minus 1, all right? So even though 2 was there's only 1, 2 ticket in this particular box, you'll notice that that because I put replacement equals true there, I could actually draw this number twice. I could draw 2 twice here. And in this particular simulation, the average is 0.625. Okay. So now in this case, in a sample size of 4, what are the smallest and largest possible sample means when sampling with replacement in this, okay? What would that be? Yes?
It would be 2 and -2.
That's right, it would be 2 and -2, okay? Now, those are very unlikely. It would be very, very unlikely for you to have gotten a 2. How unlikely would that? Does anyone know how to figure out how unlikely that is to get a mean of 2? In order to get a mean of 2, you must have had to do what? Draw 4 2s in a row, okay? And that's not going to be very likely, all right? So what we're going to try to do now is try to, we're going to try to figure out how likely or unlikely something is. All right, let's go to the next one. All right, here's an unusual sample. Suppose I tell you, okay, that on my way here to class, I went ahead and draw 4 tickets from here, and I claim I got 1, 2, 2, 2. Okay? How believable is that? And how can you tell me? So if I got 1, 2, 2, 2, 1 followed by 3 2s, that's what I claim, coming here. That sample mean would have been 1.75. So do you believe that I actually got that from drawing this, or do you think I just made up that data? Okay. So let me get a volunteer, another volunteer again. So I'm going to have you draw another 4 data, and see, can you come up here? Draw 4 data and just put it here. Put it on here. So mix this up. Go ahead, just put 4 values on there. Okay, so that's nowhere near 1.75 or larger, okay? What if I keep on telling him, keep on doing it until you actually get it, all right? Yes?
There's no way he'll ever be able to do it that way because it didn't replace it every time.
Oh, that's true. I'm sorry. That's sorry. I gave you the wrong thing. You're supposed to draw one, put it back in each time. Okay, thank you. That's a good point, okay? But, okay, so let's have him do it again one more time. Just draw one, put it there, and continue that process. But if I have him do this until he gets a number 1.75 or larger, how long do you think it will take him to do this? A day, 2 days, a year? How likely? Yeah, you're supposed to put it back in each time, okay? So yeah, put a number in and put it back in and tell me what the average is. So if he were to keep on doing that, I mean, how many times would he have to do this until he sees the number 1.75 or larger, okay? So just do it one more time and then just tell me what that number is. So, so the whole point is how long do you think it will take him if he were doing this? If it takes him like what? How long? It takes him like a minute to do this each time. How long does he have to do this in order for him to see a number 1.75 or larger? And what number do you get last time on the average? But nowhere near 1.75, right? Okay. So, of course, what I'm trying to get at this point is that, doing this thing is going to be take you quite laborious. So, the better way to do this is to do it in what? To do this in R, right? So R can simulate this data very quickly. Okay. So I could do 1,000 of these immediately. Okay. So here's what we're going to do next to show you how that's done. And then when we look at maybe a simulation of 1,000 of these, we'll see is that believable or not? Okay. Okay. So here's this command I use this command called replicate 1,000. That means I'm going to do this 1,000 times. Okay. So what did I do? I take the sample box for replace equals true. That means I put it back in. The mean tells me I take the average of it, and the replicate tells me I do 1,000 times. Okay. So now I have a vector called sample means, which has 1,000 numbers. So what I did was I just ran a command called table sample means, and these are my 1,000 samples. And what was my smallest sample mean was minus 1.5, and the largest sample mean was 1.625, and that happened 3 times. So here, this is a total of 1,000 values, okay? So even though we did it 1,000 times, did we see an average of 1.75? And the answer was, in this case, no, okay? We could actually, when we hit the probability section, we'll be able to predict how many times we would have to do this until we see a sample of, until we see a sample mean of 1.75 or larger. But this tells you, this is done through simulation, where I've simulated this 1,000 times, and nowhere do I see 1.75. What I could do at this point next, I can make a histogram. So using this next command, HIST for a histogram, which you've seen before, of sample means, I could plot the distribution. So if I were to run this thing again, I would get a slightly different distribution. But on average, I could see that between 0 to 0.5, roughly right here, is where we have our mode. Okay? If I were to calculate the average of all this thing, I'm not going to get exactly 0, because this is called this is not the theoretical distribution, but this is called the empirical distribution. So I could actually figure out how many times I got various numbers, and this is an empirical distribution. So looking at this, okay, we weren't even able to see that number 1.75. Do you think I created that data, or do you think I actually pulled those 4 numbers? What do you think happened? It's pretty obvious, right? I just made that data up, okay? So that is, so this gets back to what Dr. Nolan was saying on the other day when she talked about the Salk vaccine. Okay, remember that? So there, we were talking about 1.8 million records, and we divided up into two groups. And I think the p-value was less than 1 over a billion, which means less than, and we haven't told you how to calculate those probabilities, but what she did was she did a simulation of 50,000 times, and all 50,000 simulations, we never saw a difference as we did between the experimental group and the control group. Okay, so when that is the case, what are we saying then? We don't believe this could have occurred by chance. Okay, so looking at this thing right here, you either believe that I picked those things by chance, picked those 4 large numbers, or you could either, I believe I picked those 4 numbers by chance. But when you look at this, when you look at 1.75, this way out here, it's not very likely that I would have done that by chance. So I probably fudged the data. Okay. So a couple of things that you've learned from this is that different ways to summarize information nicely is this histogram. And if you actually want to see the individual values, you would use that table command to see how many, to see the frequency and a specific number. And lastly, if you wanted to do simulations, R is very nice in that you're able to run these replicate commands, and it just goes into the vector, and then you could do other things with it too. You can calculate averages, standard deviations, a lot of different simulations that could be easily done in R. Okay. All right. Questions? All right. So that's it for we'll end early today. Okay. Thank you.